Hello, students. Today we are going to discuss angular momentum. Going to discuss angular momentum. Angular momentum. I remember in the past we discussed linear momentum, but now we'd like to discuss angular momentum. Just recap, just to remind you that we talked about momentum in the past. I think we called it momentum, but now to distinguish from a new momentum, angular momentum, we need to call that linear momentum. Okay, so I know in the past we just say, oh, momentum, but now we want to make sure we distinguish, we differentiate it with the new momentum here. So we're gonna call that one linear momentum. The linear momentum was defined as the product of mass times velocity. I remember the symbol was P equal to M times V. That was the linear momentum, or just momentum in general. The new momentum here, the one we are going to define newly, angular momentum. Angular momentum, the symbol is usually L. We usually use L. And L, instead of having the P, stands for this L, for a rotating object. And instead of having the mass, we are going to have a rotational inertia of the object. Rotational inertia. Remember, rotational inertia depends on the mass as well as the distribution of the mass. So I here, and then we have velocity. Our velocity will be just angular velocity or rotational speed. So this is the formula for angular momentum. We multiply the rotational inertia, and then multiply by, what is this? This is a rotational speed. And as I said, the L stands for angular momentum. Okay. Now let's think about the simple case whereby we have a pendulum. Think about a simple pendulum case. How can we talk about angular momentum, or how the angular momentum formula look like for a simple pendulum case? So I'm thinking about this case whereby we have the mass that is located at a certain distance. When this is a radius here, what would be the angular momentum of this kind of object? Now, I want you to remember a few things that we discussed in the past. We discussed that L, I mean, not in the past, but that's the previous slide. L will be I times omega. That's the formula for angular momentum. And I want you to remember that for a simple case like this one, I is just given by mr squared. So the rotational inertia of a simple pendulum is mr squared. For when a mass is away from the rotational axis, such as this one, the mass is small enough compared to the length here, then we use I equal to mr squared. And then I want also to remember that the velocity of such kind of an object, the linear velocity is related to the angular velocity somehow. Remember, there's a formula we say velocity is equal to the radius or radial distance, and then times omega. I hope you remember that. Therefore, we can actually say that omega is equal to velocity over radius. So I just rewrite this equation, can be rewritten to make sure that omega is isolated, so V over R. So I'm going to take these results. I will take this into this equation, and I will take the I into this equation. So basically, this tells us that the angular momentum of a mass, like in this example, will be mr squared, That'll be the I. And the omega is V over R, like that. And if you cancel one R here, we end up with mvr. So for a simple case like this, angular momentum is given by m times velocity of the object, this one, then times the radius, this one here. This is the formula for the angular momentum of a simple case where we have the mass that has a small size compared to the radius r there. In other words, a simple pendulum. Okay, so this is the angular momentum. In this class, we want focus too much on looking at this as a vector quantity, but in other higher classes, we might want to look at angular momentum as a vector. For now, let's understand this as just the magnitude of the momentum, angular momentum, that is to say. All right. Let's see. Now we need to talk about the other related concept. The other related concept to this idea will be conservation of angular momentum, which is very, very interesting. So let's talk about conservation of angular momentum. Just like how we talked about conservation of linear momentum, we have also conservation of angular momentum. Angular momentum. Well, this idea can be explained very well by looking at an ice skater. So think about ice skater. What happens to the ice skater when they stretch their hands away like this, and then they are trying to spin. So ice skater here. Okay. So ice skater, when they spin their hands like that, then they are spinning like this way. When they spin around, oh, let me see. This looks like, let's assume they are spinning like that. And then if they decide to bring their arms closer, maybe think about, they decide to bring their arms closer. It's an ice skater. Ice. If the arms are intact position, they spin, but not that much. So as you can see, the angular momentum in this case is actually larger because the arms are spread out, and usually we say that rotational inertia, is larger. Remember that rotational inertia is larger when a fairly good amount of mass is distributed away from the rotational axis. Then you have a larger rotational inertia, and because of that, we have a smaller omega. In other words, the rotational rate will be smaller. In this case here, because the arms are brought closer to the body, and as the ice skater is spinning, we are going to see that the I will be reduced because the mass is closer to the axis of rotation, and consequently, we are going to have an increased spin. Actually, I should have drawn a bigger arrow maybe to show that it's increased spin here more than before. So you spin it faster. So that means small I, bigger omega. All right. So here we have I omega equal to I times W omega. Now remember, we had our formula for rotational inertia here as I omega. Here's the formula, I omega. So what I'm doing here, I want to tell you that I want to share with you that the product here is actually angular momentum here. That's the L. And the product here is also the angular momentum. These ones do not change, they are the same. If we can put in some conditions, we are going to see that angular momentum has to be the same. What is changing is the rotational inertia, and the angular velocity is what's changing, but the product has to be the same. And that is what we call conservation of angular momentum. The condition is that the surface must be friction, and that explains why the ice skater does this on ice surface, and nobody should stop them pushing. So in other words, if we say that the net external torque is equal to 0, that means the product of I and omega will be the same. Okay. So net external torque equal to 0, then what? Then we see that capital I omega must be equal to small I times omega large. And this condition is called the conservation of angular momentum, right? So the conservation of angular momentum says that if the net, or I should say, if no external net torque acts on a rotating system, the angular momentum of that system remains constant. Okay, that's the statement of the conservation of angular momentum. I want you to be careful there. The L is the same in these cases. What is different is the I's and the omegas. When I is small, omega has to be larger, right? So that's what you're saying here. So let me write the statement of conservation of momentum, angular momentum, then I'll close the discussion. So if net external torque is 0, let's say on a system, if net external torque on a system is 0, the angular momentum of that system remains constant. The angular momentum of that system remains constant. All right, so in other ways, well, this looks like kind of something that we can observe in so many scenarios whereby, even in general, all rotating objects, they spin faster when they actually contract. So when objects contract in general, for example, a nebula is a cloud of dust and gas particles in space. Now, when nebulae contracts, it is seen that the nebula spins faster. The reason it spins faster is because in general, when objects contract, they have a small rotational inertia, and the small rotational inertia is compensated by a larger rotational speed. That's the conservation of momentum, just in general. Whenever rotating objects contract, they spin faster. When rotating objects expand, they spin less. There's a rotational speed reduces. So in that case, you could have bigger I, small omega equal to small I, bigger omega, or you could start with small I, more rotational. If you increase the rotational inertia, you reduce this. So either way, what you are seeing here is that angular momentum is conserved. And remember, I want you to remember that it is only conserved whenever the net external torque should be 0. No friction on the surface, and nobody should stop the ice skater from spinning. In that way, the net external torque will be 0. Just like what we talked about when we discussed linear momentum, we said that linear momentum should be conserved whenever there is no external force. But in this case, we say no net external torque. For the linear momentum, we said no net external force, no net external force. The net external force acting on the system must be 0. Then linear momentum is conserved. For angular momentum, the net external torque must be 0. That will achieve conservation of angular momentum. Anyway, I'll stop here. If you have any questions, please let me know. Bye for now.